Oops. Okay, so what we're going to do is first kind of go over what our plans are for the week. Then we'll finish up that tiny little bit of Chapter 7 we had left and start in on Chapter 8. So what we're looking at for this week, Monday, Tuesday, Wednesday, Thursday, Friday, is Tuesday we're going to finish the Lewis Structure Lab. And that's Lab 11. And remember, it's after Lab 12 in your book because Jay apparently can't put the labs in the right order. And then on Thursday, we're probably going to start a lab on calorimetry. And I forget what lab that is in the book. It's either 3 or 4. And then Wednesday, of course, what we're going to do is have homework 7, whatever the last one is, due, 7F. And maybe 8A, we'll see how far we get in lecture since we're a little bit off of the lecture versus homework aspect of it. And then on Tuesday we also have, let's see, lab, not the lab, but homework 7E was due. And let's see. Haley, you didn't get one of these, so come up here if you want and grab one. Nathan, you weren't here either, were you, on Friday? So you should each get, oh, I'm sorry, actually, these are your packets. It has a bunch of slides that we had from the handout. I was wondering why I didn't have enough copies of it. I always keep an extra and then one for me because I don't memorize it. Might be in a pile somewhere. I don't know. I don't think so. I think I print them out. If you don't show up to class, I throw them away. And in fact, I'm to the point where I may stop printing them out entirely because it's a waste of paper since really only one person is doing them, which arguably, since it is Nathan, he is the one I should make get copies. So perhaps we'll do that. Anyway, going back over molecular orbitals, we'll do a little bit of review, see if we can jog memories loose for people that were here or watching the lectures. So molecular orbitals were the combination of two atomic orbitals being mixed. And what mixed means is that it's kind of like when we're playing music, we can strike two chords. Remember, electrons can be considered as waves, and then the sum of those two chords that we strike were made a new one. And what we said is that for the very simplest one, if I took an s orbital from one atom and an s orbital from another atom, kind of looks like eyeballs. Here, there's my two s orbitals and a smiley face. Anyway, I've got my two s orbitals. What that led to is it led to two different types of mixings. We could have constructive, where our electron density was spread evenly around the atoms, and so there's electron density between the atoms, and we call that a bonding orbital, in that those electrons, because they're between the two atoms, are also the attractive force that's holding those two atoms together. But we found that if we have them combined and we have destructive interference between them, then we have the electron density on either side of where the atoms are, and there's a node down the middle. So there's a node of no electron density. Therefore, there's no bond characteristics, no bonding, there's no attraction. And we call that a non-bonding orbital. And then we did the same thing for the p orbitals. And the pictures are harder to draw. That's why we have the handouts. Also, I highly recommend reading this section in your book. Your book does a really good job of drawing the pictures, showing the addition and subtraction of the waves and things like that. And so, you know, I think your book does a better job than I do just because it can draw better pictures. And it's more patient. It allows you to look back and forth between things. So then we have some rules. Well, we also talked about what we meant by well, let's see, what order do I want to do this? I guess we'll do it like this. So the rules for using molecular orbitals. The first rule is that the sum of the atomic orbitals is equal to the number of molecular orbitals. Because remember, they really are just the mixing of the individual atomic orbitals, and then they're spread out over the whole molecule. So what molecular orbital theory is saying is that we don't just share necessarily one set of electrons or two sets like Lewis structures might have said, or valence bond theory. Instead, it's saying that all of the electrons are spread evenly around all the molecules, or that, you know, if they're in non-bonding orbitals, then they really are around one atom or another, and that we can consider that sort of our picture of that. So the other thing is that we said that bonding orbitals are lower in energy and more stable than non-bonding orbitals. So when we said, for instance, if I mix a 1s orbital from one atom and a 1s orbital, so on either side is sort of an atomic orbital. And then what we did is we said that the mixing occurs and we draw our molecular orbital in the middle, that one set of those orbitals is lower in energy and one set of those orbitals ends up being higher in energy, but the net energy between them is still the same as the two individual atomic orbitals. And so we said since this was a sigma overlap, we'd call that a sigma 1s and then a sigma 1s with a star. So I guess we can say that sigma, this is more a review, this isn't really a rule, so maybe I'll just put it off to the side. Sigma meant that we had head-to-head overlap. And the sigma star meant that this was a non-bonding orbital. And so the regular one is a bonding orbital. It's just like our Hund's rule, which is basically fill low energy first, then higher. And then we also, you know, according to Hund, don't pair up until you have to. So most of the rules for regular atomic orbitals apply for molecular orbitals. And then the last part is sort of, oh, we also have 5. This was also a Hund's rule. It was basically if they're spin aligned, which, you know, we don't worry about too much. And then number 6 is we're going to define something called a bond order. And this is equivalent to what we consider a bond strength, meaning that we can mathematically calculate it. And it also corresponds to the idea of single, double, and triple bonds from Lewis structures. And the idea is that the bond order, or BO, is simply the number of or it's equal to, 1/2 the number of electrons. I can't make my symbols look right. Number of electrons in bonding orbitals minus the number of electrons in non-bonding orbitals. Meaning, take all the electrons that are in bonding orbitals that would indicate that the two atoms are bonded, subtract off all the electrons that are in non-bonding orbitals that aren't contributing to that bond, and the sum total of that is the type of bond you would expect and also the bond strength that you would expect between two sets of atoms. So let's take a look at some examples then. So if we take a look at hydrogen, that's the easiest example. There's a 1s orbital and a 1s orbital, and each hydrogen atom has an electron. And then we can draw our molecular orbitals. And actually, I'm going to draw the molecular orbitals in red, simply to keep them separate. So these are my molecular orbitals. And if I put 2 electrons in them, then I get 1 electron here and 1 electron there. And so realize that this is 1 hydrogen atom. This represents 1 hydrogen atom. And this represents my hydrogen molecule in the middle. And we would say then that that bond order is simply equal to 1/2 of 2 minus 0, or 1. So it predicts a single bond, which is good, because what type of bond does hydrogen make? A single bond, right? And then if we take a look at, say, the next element up, and we look at helium, and we try to make the helium-2 molecule, which first of all we know does not exist. So again, I have my 1s orbital, my 1s orbital, I have my molecular orbitals, and then each helium has 2 electrons in it. And so then when I fill the molecular orbitals, they're both filled. And so then if I take a look at my bond order, it's equal to 1/2 of 2 minus 2, which is just 0, which predicts no bond. Which, what do we expect for helium? No bond. We know that helium doesn't make a diatomic molecule, so we're pretty happy. And then as we go on and on, it gets more complicated because we have to draw more molecular orbitals. So for instance, if I take a look at, say, lithium-2, here now I have 1s orbitals, but lithium also has 2s orbitals. And so this is what lithium normally looks like, meaning it's got 3 electrons. And if I go ahead and fill those electrons in, and remember, the higher one is a non-bonding orbital, the lower ones are my bonding orbitals. And so if I take a look at that, I get my bond order equals 1/2 of 4 minus 2, which is simply equal to 1. So it actually predicts a single bond is possible. The other thing it also predicts is that this should be diamagnetic, meaning that there are no unpaired electrons, meaning they're all paired up. So we expect it to be non-magnetic. And then what happens, for instance, is if I look at, say, boron. Now, I'm going to start ignoring the 1s orbitals, because one of the things you should notice is that totally filled orbitals cancel each other and therefore never contribute to the bond order, or basically what that's saying is to bonding. Meaning that we can ignore the 1s orbitals. So if I take a look at boron, I'm really just looking at its 2s orbitals. And this is what all those little extra orbital diagrams are supposed to be on your handouts here, so you don't have to bother drawing them. Notice when we get to the 2p orbitals, it gets really complicated. So if I take a look at boron, it should have 2s2. Oops, wait. Oh, boron. Oh, I need to draw the p orbitals in there, sorry. Because it's 2s2, 2p1, right? Wait, am I in the right spot? I do want to be talking about boron. Yes, excellent. So here's my 2s orbitals. And it's got 2 electrons in those. But then boron also has access to 2p orbitals. So here's the 2p orbitals. And notice that the bad thing about molecular orbital theory is it quickly gets complicated in that I've got a series of bonding orbitals at the bottom. So this is my pi and my sigma 2s. And then it's got a couple non-bonding orbitals higher in energy. So this is my pi star and my sigma star 2s. And so if I put 2 electrons in that, notice that they go in separate pi orbitals down there. And so notice this predicts for my bond order of 1/2 of, let's see, I technically have 2, well, these are full, so those cancel, so we can ignore those. So really I have 2 minus 0 equals 1. So it predicts a single bond. But the other thing it also predicts is because it's got aligned spins, it predicts that it should be paramagnetic. And indeed, we see that boron really is paramagnetic, meaning it interacts with a magnetic field. So one of the things we said about molecular orbitals is they really do predict that things should be higher in energy, or that, I'm sorry, they do really predict the paramagnetic diamagnetic, or it predicts the magnetic properties of these molecules, something that Lewis structure fails miserably at, and something that valence bond theory also failed miserably at. And so the advantage to this is that it really does predict what we expect. We'll do one last example, nitrogen, since that's kind of interesting. And I also did oxygen the other day, so we can not worry about that. So nitrogen, if you look at it, has in its outer orbitals, its s orbitals are full, and then it has 3 unpaired electrons in its p orbitals. And so if I draw this diagram, 1, 2, 1, 1, 1, 2, notice that it goes 1, 2, 3, 4, 5, 6, 7, 8. Notice that if I calculate that bond order, that's equal to 1/2 of 6 electrons in bonding orbitals, 0 electrons in my NBOs. And so I get a bond order of 3, which predicts a triple bond. It also predicts that it's diamagnetic, which is also happens to be true. We know it should be diamagnetic. Okay, so that finishes up chapter 7. Molecular orbital theory is more complicated than valence bond theory, which is obviously more complicated than Lewis theory. For any molecule that has a sufficiently large number of atoms, meaning anything beyond a diatomic, this becomes really unwieldy to do. And so in the end, what we tend to not do is ever use molecular orbital theory at all, to be honest. I still want you to know it. I still want you to be able to answer a question on the test, but realize that if you had to have the take-home message from chapter 7, then that is Lewis structures and understanding those. And the rest on the valence bond theory, it's nice, it'll show up on the test, but long-term, don't worry about it. Okay, so that's chapter 7. What I'm looking at is we'll finish up chapter 8 this week, so figure probably Thursday or Friday before Thanksgiving, we will have a test over chapter 7 and 8. And I'll be honest, we'll have a test over whatever we end up covering. If we don't end up covering all of chapter 8, we still might have a test, simply because people become stupider over Thanksgiving, as far as I can tell. That week off really makes things tough for people. So it's better to get the test done out of the way, not have to worry about it over Thanksgiving, and not worry about it. So let's look at chapter 8. Here we're doing kind of a 180 in that we're going to switch talking about atoms and how things bond together, and instead we're going to start talking about energy. And the way we're going to define energy, or I guess maybe before I even just go straight into the definitions, maybe we should have a little bit of rationale why we're doing this, other than the fact that it's in your book and the state of Colorado says we have to do it. I mean, that's technically the real reason. So we've been focusing on matter, on atoms and matter for the most part. But we also know that through E equals mc squared that, energy and matter are interconvertible. We also know that most reactions occur because of a change in energy, not because the atoms are changing type. And so our real motivation is that energy is what changes in a reaction. And is what's responsible for what we consider a stable molecule. We almost always go from a high energy, low stability molecule to a low energy or high stability. And so what we're going to realize is that, and we talked about this before in chapter 3 when we looked at, or no, I'm sorry, your book has it reversed. Chapter 4 on reactions is that two things determined what if a reaction was going to occur. What we called enthalpy, which was energy, and entropy, which is the concept of disorder. And so chapter 8 is going to be on energy, and then we pick up disorder second semester, and I forget which chapter that is. It's like chapter, I want to say 12 or 13, but I tend to forget the chapter numbers pretty easily, so don't hold me to that. And so what we want to look at is both the release of energy in a reaction. We call that exothermic. The absorption of energy, what did we call that? Endothermic. We're also going to look at basically the capacity to do work, and we're going to look at the conversion of energy, and we'll also look at the flow of energy. So really, the whole idea is that we're going to look at every possible aspect of energy and try to kind of really get at understanding what's happening to the energy in a chemical reaction. So let's define some terms. Energy, and this, I guess, Gabe, I was going to ask him a question, but he's choking to death over there. Oh, I was simply going to ask you, have you guys talked about energy yet? Okay, so you should be familiar with this. The energy is basically the capacity to do work, right? The capacity to supply heat or do work. So we're going to define it in a very physicsy way to start with, which is basically that energy is simply equal to heat plus work. That's going to be our basic equation. Now, we're going to give it some fancy letters. We're going to set some conditions on what type of work is allowed. We're going to, expand on that, but we're going to basically keep it pretty simple. The energy comes in two types of energy. And Gabe, you should have also covered this already, or are going to cover it. I don't know. The two types of energy are? Ooh, just wait, kinetic. Let me write this down. Kinetic energy, which forever after shall be called Ke because I'm lazy. What else did you talk about? Oh, yeah, we ignore gravity. Thermal and potential?
Yeah, well, the gravitational potential and
Okay, so we are going to define things a little bit differently in that we're going to lump thermal energy in with kinetic energy to a certain extent since it's due to the motion of atoms and vibrations and things like that. We're going to take potential energy, including gravitational energy, which is a good way to think about it too, and lump it into the stored energy in chemical bonds, or basically stored energy due to position. So about the same. Kinetic energy is basically the energy due to motion. And, that motion can be something as simple as, a bullet or a car, or in the case of molecules, we're generally going to be talking about rotational, vibrational energy. And so rotation means the molecule is tumbling in space. Vibrations mean it's vibrating like a spring. And then for potential energy, that's going to be basically stored energy due to either position, and that really is what physics would call gravitational, and also chemical energy, meaning stored in bonds. And obviously we're going to kind of stick towards that second definition, or storing the energy in bonds. And we can have a few equations to describe some of these. The easiest one to define is simply kinetic energy, where kinetic energy is simply defined as 1/2 mv squared, where m is simply the mass of an object. And since we're in SI units, we usually measure mass in kilograms. Velocity is measured in meters per second squared. And so that gives our units for energy as a kilogram.
Velocity's not square, it's already kidding. Is it right?
Are we allowed to square velocity?
You were meaning acceleration. I was like,
No, we're not going to mess with acceleration. And so you thought I had meters over second squared? Not, yes. No, we have to square it. So meters squared over second squared. So this is technically the unit of energy. But that's a messy unit. So chemists, and I got to be honest, probably other people too, simply redefine that as a joule. So that stands for 1 joule. And it's basically a kilogram meter squared per second squared. Sometimes in an equation we'll use it as joules. Sometimes in an equation we'll actually kind of blow it up. The other standard unit that you'll sometimes see is called a calorie. And 1 calorie is equal to 4.184 joules. Calories tend to be used in nutrition. And so, be aware that calories are there, that calories exist, but that in general, 9 times out of 100, we're simply going to use joules for our unit of energy. And if you have a question that says calories, just realize that a calorie and a joule are kind of the same thing. It's kind of like realizing that a foot and a meter are the same thing. They're measurements of distance, right? It's just how much distance they measure is what's different, right? Same thing with calories and joules. They're both energy. It's just a question of how much energy.
are you going to include kilocalories?
Well, we can talk about kilojoules, but a kilojoule is just 1,000 joules, right? Because kilo means the same no matter what. Same thing with a kilocalorie is equal to 1,000 calories. Now, here we do have to actually mention, since you brought it up, that retarded people talk about capital C being a kilocalorie versus lowercase c being a calorie. And a big C is a kilocalorie. No, we stick with joules. This calorie stuff is bullshit. Just because you probably couldn't tell the difference between my lowercase and the capital C anyway. No. So we can, of course, calculate the kinetic energy of anything very easy. Calculating potential energy is pretty darn tough. And in fact, we don't tend to ever actually calculate potential energy. Instead, what we simply calculate is changes in energy, or changes in the potential energy. And so very rarely will we, well, in fact, never will we actually calculate the absolute energy of something, except for, do we do it? Yeah, we do it for one minor case as an example in the chapter on thermodynamics, where we talk about disorder and entropy. We actually calculate the absolute energy of something, but in general, we don't bother. So the other thing that we need to talk about when we're looking at energy is how we measure energy. And so there's 2 terms that we tend to use that people tend to get mixed up with a lot. And I got to be honest, before I started teaching chemistry, I would use these terms interchangeably, completely. Meaning temperature and heat meant the same thing to me. Like, for instance, you ask, how hot is it out, right? Really what you should say is, what temperature is it out? To be technically accurate, that there really is not a hotness out there. What hot and cold really refer to are the differences between what you're currently at and the other object you're comparing to. You would say the other object is hot if it has a higher temperature than you do have. And then so those words get kind of mixed up, and so we have to be really careful. Turns out that heat is an amount of energy. And it can only be measured as it's transferred between two objects. Meaning, we never measure the absolute heat content of something. We simply measure the transfer of heat between objects. Calculating the actual total amount of energy or heat in something is very tough. Heat has units of joules. And so a lot of times we use heat and energy as interchangeable terms, even though technically they're not. Whereas temperature is a number that's related to the hotness or coldness of an object relative to another. And what it's actually related to is or it's kind of proportional to the average kinetic energy. Of an object. And of course, temperature has units that we're familiar with: degrees Celsius, degrees Fahrenheit, or Kelvin. And we'll stick with degrees Celsius or Kelvin. And the two things, or the way I kind of remember the difference between energy, heat, and temperature, is that heat is an intensive property. Do you guys remember what intensive meant? This is the very first, almost second lecture, maybe the first lecture that we ever had in class. So it's kind of like, for instance, mass and volume are examples of intensive quantities, but densities is an example of an extensive quantity, right? So intensive means it depends on the amount of matter present. Think about it this way. If I compare a cup of coffee to a swimming pool, which one has more energy in it? Yeah, the swimming pool, because it's got more matter in it probably, right? Or would you rather, which has more heat? A single cup of coffee that's boiling or an entire swimming pool is boiling? Well, the swimming pool has a lot more energy, right? But if we compare that to temperature, temperature is extensive, meaning it does not depend, does not depend on the amount of matter. And so the temperature of both is 100 degrees Celsius. Well, okay, that's probably a lot hotter than my coffee or my swimming pool ever gets, but two objects can have the same temperature, right? But they can have a different amount of energy, right? An analogy to that people use, I personally kind of like just remembering the temperature and the swimming pool idea. But if I take a look at another analogy, and this is kind of continuing my little bullet list, so here's heat and here's temperature. We can think about it like test grades. So the total number of points in a class is kind of like the total amount of heat that we have in an object. The temperature is basically the average score that you have in class. So it's an average of all the points, or average kind of what you got. That's one way to kind of think about it. The other way to think about temperature is it's kind of like density, in that temperature measures the concentration of energy, while density measures the concentration of matter in something. I don't know if that helps make it more sense or not. Usually, to me, the easiest way to keep the difference between heat and temperature is heat is an amount of energy, temperature is simply the amount of energy in an object compared to basically the size of an object, kind of like density, meaning, you know, if I have a small object, it's going to be very hot. If I have a very large object with the same amount of energy, it's going to be very cool compared to a small object with, you know, the same amount of energy. And, or think of one as intensive and one as extensive. So, we can take a look at energy. We can take a look at, you know, measuring changes of energy. And really, the first thing that we want to do for that is the first law of thermodynamics. Now, we also called this conservation of energy earlier. But honestly, to me, well, I personally like the phrase conservation of energy, mostly because there's 3 laws for thermodynamics, and I can never remember which one is numbered 1, 2, and 3, whereas I can remember what conservation of energy means. But it basically says that energy cannot be created or destroyed, but it can be converted from one form to another. And so what we're generally going to be focusing on is basically how it can be converted. An example of that, you know, is we can follow a whole string of what happens to energy. In fact, heck, we can even start before light. We can have fusion in our sun that produces light energy in sunlight. And then, of course, a plant can convert that to stored energy in a plant, which can be converted to stored energy in fat, meaning a cow or something like that, meaning a cow can eat the grass. We can eat the cow, so that turns to stored energy in you. You can climb a mountain, which converts that energy eventually into waste heat and the ability to, and potential energy, because as you're going up in altitude, you're gaining potential energy since you can do work coming down. So energy can be converted in all sorts of ways, and we can kind of follow those ways by, you know, how we're looking at them. Okay, so, and this is all set up, I should point out, to kind of things that we're looking at, you know, in other things. So, in order to follow the transfer of energy, we need to define some things. So the first thing we're going to define is the system. And the system is basically what we observe, or really I like to think about it as what we care about, meaning in general it's a chemical reaction. We're not actually going to do, I think, a lab with chemical reactions. We're instead just going to simply look at heat transfer from metal objects. And so it might be the metal object and what we call our surroundings. And the surroundings is basically everything else. It really means, like, for instance, it might be the beaker that we're doing the reaction in. Technically, it really is the entire universe surrounding us. So we're always going to be drawing little boxes like this, you know, where we talk about our system, and then everything else is our surrounding around it. And so we'll show things going into and out of the system and things like that. And there's 3 types of systems. Of which we'll particularly pay attention to just one of them. The first is what we call isolated. That means there's no exchange of mass or energy. between the system and the surroundings. So we quite literally just have a box, oops, it represents our system, and then outside the box is what we call our surroundings. We're going to have a closed system, in which case there's no exchange of mass, but there is an exchange of energy. So for instance, that means that our box looks like this, and into and out of the box we'd allow energy. You can think about this basically as a sealed beaker, meaning that energy is allowed to escape in and out of the beaker, and we do it like that. And of course the last system, and the one that's hardest, is an open system. That's where you can exchange mass and energy, and so you end up with a box that looks like this. We can have energy going in and out, but we're also allowing mass to exchange. Now we technically tend to stick with system 2 and not worry about any of the other more complicated systems at all. And then the other thing that we want to think about is the signs, or for heat transfer. And we've already talked about this a little bit, but basically we're going to define exothermic as the energy of our products is less than the energy of the reactants, or we have heat as a product in a reaction, so we would write reactants go to products plus energy. Or in the terms we're thinking about it now, we're basically saying heat is transferred from the system to the surroundings. And so we're going to give any type of change that's an exothermic change a negative sign, because the system loses energy. And so if I draw a diagram like this, and there's my system, then the arrow going out should have a negative sign associated with it, and the arrow going in will have a positive sign associated with it. And so, of course, endothermic is the exact opposite of exothermic. So the energy of the products is higher than the energy of the reactants. Heat or energy is a reactant, so we say reactants plus energy goes to our products. Heat is transferred from the system, from the surroundings, to the system. And therefore, any change in energy that we measure should be given a positive sign. A positive sign. Because the system gains energy. So really, what we should realize is that the signs are all based on the system, meaning the system is what we care about and everything else is different. We can make the same statements for work being transferred into or out of a system, but we're not going to really worry about that too much, mainly because it follows the exact same signs. Okay, one last thing to talk about, and wow, it's already 10:17, so that's good timing, is state functions. So a state function is a property that's determined solely on the present state of the system. Determined solely on the present state of the system, regardless of how it got there. So an example of state functions are things like position. So if I have a mountain climber, if he's at position A, we don't care how he got to position A, that's just a measurement, right, of his height. But if I ask how much energy did it take to climb from A to B, that matters, right? On the route, or wait, so position and, let me think, make sure I'm not screwing this up. I'm picking a bad example, maybe. Yeah, so how much energy did it take to climb to B varies, right? Or we could also, I like a better example. For instance, if I am traveling from Rangeley all the way back home to Mankato, Minnesota, the distance between Rangeley and Mankato is an example of a state function, meaning it doesn't matter. Now, the distance driven is not equal to a state function. Or actually I call them NSFs, not state functions. It's my own terminology. So, you know, if I take this way home to Minnesota versus a straight line versus if I end up zigzagging back and forth, obviously the distance traveled changes, right? So does the time spent, the amount of money spent on gasoline, and etc. And it turns out that things that are state functions are nice to measure, meaning pressure, volume, temperature, and energy are all state functions. Things that are non-state functions are things like work, heat, time, money. Here we could say position, distance traveled. The key is that state functions are reversible. Meaning that the net change is 0 for a completed path. Or what it's really saying is that any changes are path independent. A good example of that is if I have a cup of water at, say, 25 degrees Celsius, and I heat that cup of water to 50 degrees Celsius, and then I cool back to 25 degrees Celsius. So this is my start This is my n. For instance, the temperature of that net change is 0, right? So temperature is a state function. It doesn't matter all the different temperatures that you went between. I could have heated it, I could have cooled it down to minus, 0 to 0 degrees Celsius and heated it back up. The end result is the change in temperature is still 0. But the change in energy, or the change in the heat, or the energy required to do that, depends on the path. So the idea is that we want to measure, or when we do chemistry, we want to focus on state functions, because those are the things that are path independent. Those are the things that we don't really want to kind of have to worry about, or we don't need to think about as much as we're doing our things. I think that's where we're going to end for today. I don't think I forgot any definitions on the homework. I don't think I forgot anything terribly important. So again, Tuesday we're going to work on the Lewis structure lab. On Wednesday we're going to say 7F and 8A are due. And then, yeah, we didn't even get to 8B, which is fine. One of the things that I find tough about this lecture is it's almost all definitions, which I got to be honest is boring and hard to tell if you're doing it right. What we're going to find is the next few lectures are all going to be math and doing things, in which case I think it's always easier to tell if you understand it because you can actually go practice it. So let's call it quits for today. Do I want to keep my ink presentations? Yes. Oh, I should turn off the thing so I'm not talking to it anymore.